Hola, chaps. Mr. Turek here, wanting to do a section about CP physics, simple harmonic motion. It's not normally part of CP physics, it's normally part of AP physics. There's a couple of you, two or three, who are taking a calculus course. So I'm going to put this section in here to sort of guide you through where some of this stuff comes from, but the equations and relationships I'm going to write down apply to everyone in CP physics, if you can follow along. All right, so simple harmonic motion is any kind of motion that repeats on a regular period of time. So a planet going around the sun in a perfect circle would be simple harmonic motion. A pendulum swinging back and forth would be simple harmonic motion. A mass tied to a spring would be simple harmonic motion. Now, mathematically, all these examples have a couple of features in common. And mathematically, it lets us build a relationship that describes each one of them in sort of a similar format. So to try to get you to discover that relationship, I'm going to work with a mass on a spring. So this represents a wall. This is the floor, and there's no friction. This represents a spring, and here I have a mass that I'm going to attach to the spring. From school, I have one of the spring scales that we normally use in our classroom. This one is the House model, and you can see the scale on it. I suppose you can read that. It shows here's 0 newtons, 1, 2, 3, 4, 5 newtons. The scale here of dynes is not something that we use anymore, so you don't need to worry about the conversion of what is a dyne. It has to deal with something the interested reader is left to look it up if you're interested. All right, so when this thing is hanging vertically, the weight of the spring scale itself makes this thing rest at about 0. And what I want to point out to you is that this spring obeys something called Hooke's law. Robert Hooke was a guy who studied springs and came up with a discovery that said that for some materials, not all materials, it works out that when you apply a force to pull on this, maybe it should go like this, apply a force to pull on it, it'll stretch the spring a certain amount, and if you double the force on it, it'll double the distance that it stretches. In other words, the force on the spring is directly proportional to some constant times the distance that you stretch the spring. Now, it always has to be a restoring force, and we show a restoring force in physics by putting a minus sign in front of all this. That means the direction is back towards 0. So if I had a slinky and I were to pull it apart, let's say I move that in the positive x direction, then the restoring force would try to make it snap back to 0. So the force would be in a negative direction. If I compress the spring, moving it in the negative x direction, then the restoring force would be trying to push it apart. It would be a positive restoring force. So it's always opposite the direction of its position. So if it's got a positive stretch to it, it's a negative force. If it has a negative compression to it, then it has a positive force trying to push it apart. Mathematically, that is a key part to creating a mathematical model for simple harmonic motion. Now, what I'd like to point out to you is that this spring scale pretty much obeys Hooke's law. So I have here one of our protractor rulers, and I'm going to set it down on the 0 point of the spring scale, and perhaps, I don't know if you've got enough capability here to figure this all out, but looks like you have enough contrast and everything, you can actually make this out. So what I want to point out to you is that essentially every mark of an increase of 1 Newton of force corresponds to the same displacement distance physically down the length of the scale. In other words, when you look at the readings here, If this distance is 1 Newton, so is this same distance, this same distance. Each of these distances are the same physical displacement along this scale. And we could measure it in this case and say, all right, so if I put 0 centimeters at 0 Newtons, it looks like it's, I should put this where you can actually read it, huh? It looks about like 5.8 centimeters corresponds to 5 Newtons of displacement. If I can do this in a way that you can see it without sliding too badly, about 5.8 Newtons, I'm sorry, 5.8 centimeters physically along the ruler corresponds to a force of 5 Newtons of force to stretch the spring scale. So that is a method by which we can work out the value of the spring constant. K, the spring constant, was a force of 5 Newtons stretched the spring scale by 5.8 centimeters, which I'm going to convert directly into meters just by moving the decimal point twice. So 0.058 meters represents 5.8 centimeters. Now, a quick calculation, 5 divided by 0.058, beep, beep, beep. And in this example, the spring constant, K, I get a value of, you can almost see it, 86 newtons per meter. That is the value of the spring constant for this particular model spring scale that we have in our classroom. When I hang an object vertically on a spring scale, so if I were to draw a ceiling and hang a spring scale from the ceiling and hang some mass M from the ceiling, the spring scale will stretch. And if I measure the distance that it stretches, I'll write that as delta y. If I were to do a free body diagram, a force diagram, what happens as the spring stretches, there's a stronger and stronger force trying to get it back to zero. If I double the distance I stretch the spring is going to pull twice as hard to try to get back to zero. So when I hang something, two forces go to work on it. First is the force of gravity, and that is equal to the weight of the object, m times little g, 9.8 meters per second squared in metric units here on this planet. Meanwhile, as the weight pulls the spring farther and farther apart, the spring force starts to pull it with greater and greater force upwards, trying to stop it from falling down, trying to stop it from stretching. Over time, these two forces will become equal. If the weight is greater than the force of the spring will stretch. And once the force of the spring has grown to equal the weight of the object hanging from it, then these two forces are equilibrium and the object will not be accelerating. If you do it slowly, the object will be at rest. And this force of the spring is given by Hooke's law, a restoring force. The spring constant times the distance that it stretches or compresses the spring. So this is always measured from the rest length of the spring. I could have a spring that is 10 centimeters long when it's at rest, and I tie one end to a wall, and when I stretch it, so now it's 11 centimeters from the wall, we would say, oh, the value of x, the distance that the spring is stretched, is not 11 centimeters, it's 1 centimeter. Okay, so the distance that the spring stretches, that force increases until it becomes equal to the weight of the object hanging on it. So I can set these two forces equal to each other. The spring constant times the displacement times the distance that the spring stretches is equal to the weight of the object hanging on it. And so this allows me to calculate the value of the spring constant if I knew the weight of the object that I'm hanging from the spring and if I measure the distance that the spring stretches under that condition. So this is one way to determine the spring constant. If someone hands you a spring and a weight and a ruler and they say, go tell me what the spring constant is, that's how you would get it. All right, so I mentioned the word calculus as I started this, and it's coming. So the 2 or 3 of you who are in Calc AB, this is something you should be able to follow along with. And it goes like this. In the world of calculus, we would say that I can write position as some function of time. And in CP physics, we had this as well, but we didn't use calculus to work with it. In CP physics, we said velocity is the slope of the graph of a position time graph. So if I had a position time graph that looked like a parabola opening upwards, then the velocity, the slope would start at 0 and it would increase in a straight line, becoming faster and faster in the positive direction. Well, that's algebra based. In calculus, you would say that the velocity is the first derivative of the position. Okay, so in calculus, we could write that as x with a dot on top of it. So here's how I had it in college. The dot means the first derivative with respect to time. In CP physics, in the fall term, we studied acceleration as the slope of velocity. So in the same example, if this was an upward opening parabola starting from the vertex, this is a linearly increasing diagonal line, then the acceleration would be a positive constant in this example. So here's the x axis, here's the 0 axis. And the slope of this would be a positive constant value. Well, in calculus, if this function is the slope of that function, then that means acceleration is the derivative of velocity. And that means acceleration is actually, I shall write it this way, is actually the second derivative of position with respect to time. So I represent that with a double dot above the function for x position as a function of time. All right, so what have we got here? We have a situation where the restoring force is also Newton's second law. And so I want to remind you, Newton's second law, you love Newton's second law. Newton's second law said F equals ma. The net force applied to an object is the product of the mass of that object times its acceleration. You miss it. You wish I gave you a pop quiz on there right now. I know. But this Hooke's law restoring force is the net force for this mass on the spring. There's no other force acting on it. No net force, I should say. Of course, the force of gravity is acting on it. The normal force is acting on it. It's a frictionless horizontal surface. Those two vertical forces cancel. And now the only net force acting on this mass on the spring is Hooke's law, F equals minus kx. So that means this equals minus kx. By Newton's second law, the force of a spring is what is accelerating the mass at the end of that spring. Now, using this spiffy notation, where I point out that the acceleration is the second derivative of position with respect to time, I could write this as mx with a double dot on top of it, meaning it's the second derivative of position with respect to time, is equal to minus k times x. Now, x is a value in position for you in CP physics, but for calculus students, it's a function of time. And when you get to college, and please go there, you can take many math classes. You can take an entire math course studying ordinary differential equations with constant coefficients, such as this one. And what that means, it's quite a mouthful, is that mathematicians have discovered a class of solutions to this that says, what kind of equation could I start off with such that after I take the second derivative of it, I will have a negative version of the original equation eh, adjusted by some sort of constant. So I suppose I could write this as the second derivative is equal to minus k over m times the original function. And here I'm trying to make it clear that this is a function of position as a function of time. This is something that's not going to be obvious to you in high school, maybe not, even if you are in calculus. But the mathematicians have discovered there are a class of equations that satisfy this condition. Again, the condition is I start with some function. When I take the slope of that function, that is equal to some negative value times the original function. And if in your Calc AB, you probably recognize what the solution is. The solution is the cosine function. So if I represent position as a function of time by some amplitude times the cosine of an angle, which generally changes over time. So here I'm using a symbol for the angular frequency times time. Those of you who are in calculus, hopefully you've encountered that the first derivative of the cosine function is the negative sine function. So in this case, we would get negative omega, because that comes out from here, times A, the amplitude, times the sine of omega t. And I didn't want to burden you with it, but there's actually a phase shift that goes in there as well. I'm not going to torture you with a phase shift at this time. So don't worry about it. But if if you really care, there is a second term in here. It's just a constant. Another way I could have said that right now is to say that the general form includes B times the sine of omega t. That's the same effect as having a phase shift. Again, this is fun. I actually enjoyed this course a lot when I took it in college and set boundary conditions equal to 0 and took care of things. But for you, for now, let's just focus on this one solution and take the derivative of this function. So when I take the derivative, which is now taking the second derivative of the original function, another omega is pulled out in front. The derivative of the sine does not change signs. So the derivative of the sine function is the positive cosine function. So negative a omega squared, I just reversed the order for no reason, times the cosine of omega t. Ta-da! This is a negative constant times the original function. Okay, so let me try to write it that way. This is equal to negative a omega squared times, I guess I just need to write it again, cosine omega t, which means negative omega squared times the original function of t. Ta-da! The original function was a cosine omega t. So this class of mathematical models satisfies the physics that comes out of Hooke's law and Newton's second law, F equals ma. Hooke's law, Newton's law, working together leads to a class of mathematical models that use trig, the sine and cosine functions. You may have studied sines and cosines in your math course. So here's a time axis. A sine curve begins at 0 radians, and then goes up to a value of 1 when it gets to pi over 2 radians. Then it goes down to 0 at pi radians. Then it goes down to a value of negative 1 when it gets to 3 pi over 2 radians. And then it goes back to 0 when it finally gets to 2 pi radians, and then it repeats. This is the sine function. The cosine function is like the sine function shifted by 90 degrees. So if I made this 0, the cosine function would be starting off at a value of positive 1. At pi over 2, it goes to 0. At pi, it's negative 1. At 3 pi over 2, it's back to 0. And when it gets back to 2 pi, it's back to positive 1. So this would be the cosine function starting from 0 to 2 pi. This would be the sine function from 0 to 2 pi. Well, I certainly have more to say and explain to you, but this is a lot to take in for the moment. I'm going to keep going though, right? So things I want to explain and talk about from here. So mathematically, you've had some equations thrown at you in CK12, and I'm trying to make some of them clear as to where they came from, their origins. So let me just try to start a little bit fresh from here and say, when you have gone through a period of time equal to 2 pi, you have gone through one period of this trig function. So when the angular frequency times the period is equal to 2 pi, that means you've gone through one complete cycle in this amount of time. So, for example, if the period were 2 seconds, then the angular frequency would be pi radians per second. So here we're not working in degrees per second right now, we're working in radians per second, making things work out that way. So as an equation, the angular frequency, by the way, this is pronounced omega, the angular frequency omega is equal to 2 pi divided by the period. But wait, there's more. You might remember that when I clap my hands, if the period of time from one clap to the next is 0.2 seconds, all right, then the frequency is the reciprocal of that. If the period of time for me to clap my hands from clap to clap was 1/5 of a second, that means the reciprocal of that was I clapped my hands 5 times per second. Frequency is the reciprocal of the period. So I could substitute frequency for the reciprocal of the period here and tell you that the angular frequency is equal to 2 pi times the frequency. All right, let that sink in for a moment. There's some logic to this, trust me. It says when I go through one complete cycle, you have either the sine or the cosine. I will have also gone through 2 pi radians. So if my frequency is 1 cycle per second, then my angular frequency would be 2 pi radians per second. And if my frequency were 10 cycles per second, my angular frequency would be 20 pi radians per second. So there is some logic to this equation that I'm sharing with you now. So these are things that we would probably have on your CP Physics reference sheet. Although I'm not sure it's currently on there. All right, so other stuff to share with you. What comes out of this stuff about the acceleration being this and that? So among other things, the velocity as a function of time, that first derivative, is equal to negative a omega times the sine of, let's say, omega t. Again, I'm ignoring a phase shift. So what this is saying, first of all, the trig functions sine and cosine, they vary between a maximum value of positive 1 and negative 1. So when they say the maximum velocity that it can have, you can usually ignore when that occurs and just say it's at the point where this evaluates to a value of plus 1 or negative 1 if they ask for the magnitude. So you don't usually have to figure out at what moment something happens. When they say the velocity is a maximum, that would mean that you're at the value of the trig function, whether it's the sine or the cosine, that is at its extreme, and it can only be as great as positive 1 or as low as negative 1. So it's at one of these extremes. And you could usually just say, oh, let's just treat this as being a value of 1. So the maximum velocity is equal to the amplitude times the angular frequency. The same thing could be said about acceleration. So if I knew the amplitude and I knew the angular frequency, I could also calculate the value of the acceleration. Now, I see I should probably put these onto a graphing calculator to display, but I will try to make the point this way. At the point where the position is a maximum, and for consideration, let's consider a mass swinging on a pendulum. So, or heck, let's stick with the mass on the spring, horizontal. So I have this mass on the spring, and I'm going to pull it to the right and let go of it. So just at the moment I let go of it, its velocity is 0. Just like when I dropped an object in the fall term, at the moment I let go of it, the velocity of the object is the velocity of the hand that was holding it. And if the hand that was holding it was 0, then the initial velocity of the object is 0 at the moment you let go of it. Same thing is true with Hooke's law here. At the moment I let go of something that's being pulled, stretched by a spring, the object is at 0 velocity initially. At the same time, the force is at its maximum value. And this force is the net force, Newton's second law, trying to accelerate this thing. So because F equals ma and x is at its maximum displacement, the acceleration is also at its maximum value when the mass is not moving. The displacement, maximum value. The velocity, 0. The acceleration, maximum value. Half a cycle later, when the spring has finally stopped getting back to its equilibrium length, that whole time it was accelerating this mass, making it go faster and faster and faster. And at last, it got to 0. And in the CK12, it says, okay, but it's got inertia. It's going to go blasting through that. True. But here's what I want to point out while it's passing through 0 length. When it's at its rest length for this mass that I let go of, and now it's zooming through 0, 3 things to notice. 1, the position is now 0. 2, the velocity is at its maximum value. The speed is as fast as it's ever going to be going. And 3, because it's not being stretched or compressed, the acceleration is 0. So those 3 things are all true as this mass goes through its equilibrium position. And it's going to go through it, go the opposite side if there's no friction, equal distance, stop, go back, shoot to equilibrium, go back to the starting point, and oscillate back and forth. So this is a part of physics that we normally don't do in CP, but we always do it in AP physics. Now you can see that it's a little bit complicated getting you to the point where you can do that. All right, so what else do I want to share with you right now? For everything to work out correctly with this mass on a spring, K over M, if I go back to these notes here, K over M is omega, the angular frequency. Wow, so that's big news. And there's a square root that goes in here. This is actually omega squared. So just to write that here, we can see it. Omega is equal to the square root of K over M. And that means if I were to give you a physics problem and I said, oh, okay, I have a spring constant of 86 newtons per meter, and I hang on it a mass of, let's say, 250 grams, which in your head you should realize, oh, convert it to kilograms by moving the decimal point 3 places to the left, 0.250 kilograms. And I would ask you, so what is the period of oscillation for this? And you would say the period of oscillation is equal to 2 pi you can see that from here. The period of oscillation is equal to 2 pi divided by omega. Well, if omega is the square root of K over M, I guess I shouldn't do this too fast, right? Divided by the square root of omega. I just did that wrong, right? 2 pi divided by omega. Sorry. Well, so that is 2 pi divided by the square root of K over M. And hopefully you know that 1 over A is equal to A, and that 1 over B over C is equal to C over B. I guess I'll leave it to the interested reader to prove to himself that you know how to do fractions correctly. So, period T is equal to 2 pi times the square root, and now instead of dividing by k over m, I'm going to multiply it by m over k. And this is the formula for the period of oscillation for a mass on a spring. Period of oscillation for a mass on a spring. I don't want to zoom in too much. Okay, so back in this example, the period for a 0.250 kilogram mass that has an 86 Newton per meter spring constant should be wow. I have a period of 0.3, I'll call it 4 seconds. And the frequency being the reciprocal of that means a frequency is, call it 3.0 cycles per second. Well, as it happens, I have the equipment where I could set this mass up on a post and hang a 250 gram mass on it and let it go and watch it oscillate. So let's see if I can make that happen. And I think for now, I will stop here.
Hola, chaps. So, what I've done is in part of my office, I've brought in 3 different springs from school. And the one that we were just looking at is the old house on the left there. In the middle, I have another old house and then a Viking Junior on the right. So these are 3 different spring scales with 3 different spring constants. And what I have done is on the first one, I am currently hanging a mass, which I want to point out to you consists of 2 parts. First is the hanger itself, which is labeled at 50 grams of mass. And secondly, I'm taking a 200 gram mass and hanging it on it. Total 250 grams. And what I'm going to do now is hang it from the spring scale. You should know by Newton's second law, F equals ma, that it should stretch it an amount of 0.25 kilograms times 9.8 meters per second squared, which works out to about 2 point something newtons. And sure enough, there it is. So to complete this demonstration of the calculation you had just done, I'm going to maybe zoom out a little bit more, pan up a little bit, so that you can see the oscillation of this mass in real time as I stretch it and then let go. The period of time for it to go up and down seems to be close to our calculation of about 3 cycles per second. All right. Ciao. Here it is one more time, and I'll have my stopwatch going next to it so you can kind of see the relationship between the two. So first we get it moving, and then you time it. Ciao.